Swayam Prabha. Digital India. Educated India.
Welcome to Chapter 3. In this chapter, we'll cover assembly language, which is a vital link between the hardware and software. Just to reiterate, this is Chapter 3 of the book Computer Organization and Architecture, and the slides are meant to be used along with the book, otherwise the learning will remain incomplete. So let's first discuss an overview of assembly language. Subsequently, we'll discuss the syntax of assembly language. We'll design a simple assembly language of our own called the simple RISC assembly language along with its instructions and instruction set architecture. Subsequently, we'll move on to functions and stacks, an advanced concept in assembly language, and we'll discuss the encoding. So let's first define what is an assembly language. So an assembly language is a low-level programming language. So we'll discuss what is high-level and what is low-level. So a low-level programming language uses very simple statements where typically one statement corresponds to a single machine instruction. So these languages are specific to the instruction set architecture. And so, for example, C or Java can run on any kind of a processor. However, an assembly language is specific to only a particular processor or a particular family of processors. For example, it is possible to run C. Let's move to a different media. For example, it is possible to run a C program on both an Intel machine and an ARM machine. However, Intel has its separate assembly language syntax and ARM has its separate assembly language syntax. So we'll discuss what it is. So C is a high level language because the concepts are at a very high and abstract level. And also, if this is a C program, a single statement in the C program can actually be many machine instructions, not one, but actually multiple machine instructions. A sequence of zeros and ones, multiple instructions. Whereas, in an assembly language program, a single statement typically most often corresponds to a single machine instruction. So this is the vital and the most important difference between a high level language and a low level language. So this C would be an example of a high level language and an assembly would be an example of a low level language. So actually an assembly language is not a single language, it rather refers to a family of low-level programming languages where each instruction set architecture has its own assembly language. For example, an Intel machine like the one that's running on the desktop right now has its own assembly language. You can call it Intel assembly. Similarly, an ARM machine, an ARM processor, which has a separate ISA, a separate instruction set architecture, has its own assembly language. Right? You can call it ARM assembly language. So has its own separate ARM assembly language. So different processors, different family of processors have their own assembly languages, and each assembly statement corresponds to typically a single machine instruction. So we can think of it as a language that is very, very close to the hardware. So a typical assembly statement has two parts. It has an instruction code which represents a basic machine instruction, something like add or subtract or multiply, and it has a list of operands. Let us now take a look at the popularity of assembly. So I have a browser window open which shows the popularity of the most common programming languages as of July 2016. So the first three are usual suspects, Java, C and C++. But let's scroll down to the 10th entry. The 10th entry is actually assembly language. Again, assembly language is not a single language, it's a family of languages where each processor family has its own assembly language. But we see that from July 2015 till July 2016, assembly languages together are the 10th most popular language among all programming languages. So this means that it is a very, very important language for students to learn, and they should be familiar with at least one flavor of assembly languages such that they can program hardware much better and also understand how compilers and assemblers really work. So that's why it makes a case for at least learning these languages. One reason for the popularity of assembly languages is that we have many small devices today. For example, there are small controllers in almost everything that we use. So nowadays there are smart lights that sense if a user is in the room, they turn the light on, otherwise they turn it off. So this is actually an advantage of very small hardware, and these small pieces of hardware are not programmed using high level languages, rather they are programmed using assembly languages for the reasons of efficiency. So let's introduce a term now called assemblers. So assemblers are programs that convert assembly language programs written in low level languages to machine code, a sequence of zeros and ones, essentially convert an assembly language program to a binary. So examples of these would be for x86, NASM, TASM and MASM are three very popular assemblers for x86 ISAs. There are similar popular assemblers for ARM as well. The readers are requested to take a look at the website of the book to get an idea of assemblers for different assembly languages. So on a Linux system, it is possible to generate an assembly file. It's very easy. So we need to run this command gcc minus capital S and the name of the C file or the name of the C++ file. So say the name of the C file is filename.c. Its assembly file name will be filename.s. That is its assembly representation. So what gcc minus s does is that it converts a C file, it compiles it to produce an assembly file. And once an assembly file is generated, you can open it in a text editor and see the details of the assembly code that has been generated. Then to generate a binary, we can run the same gcc command once again and run the command gcc filename.s, which will generate a binary called a.out. And then running the binary is very, very easy. What we need to do is that So running the binary is very easy. So in Linux, it is just as simple as /a.out. So in this case, what we see is that if we have a C program with the name filename.c, a compiler converts it so the compiler command is gcc minus capital S. That converts the C file into an assembly file. That's filename.s. And the filename.s can be further converted to a binary which the processor can understand, a sequence of zeros and ones, via using the command gcc. So this holds in a Linux system. It will also hold on a system with Mac OS X with code blocks installed. On Windows, there are different commands, so I'll not get into that. So let's now take a look at the importance of assembly language from a hardware designer's perspective. So learning the assembly language is the same as learning the intricacies of the instruction set, because every assembly language statement corresponds to a single instruction. So once a hardware designer knows the format of assembly language, he pretty much knows what is to be built. So what is the interface between software and hardware, which makes it easy to design hardware as well. So now let's start with the nitty-gritties of assembly language, but let's go back to chapter 1, where we had discussed the structure of a von Neumann machine. So von Neumann machine had the CPU at the center. So the CPU was at the center. It was connected to memory. The memory contains data as well as instructions. And the CPU is also connected to I/O devices. Inside the CPU, we have a control unit, an arithmetic logic unit, and a set of registers. So the registers are named storage locations. In ARM assembly, they are called R0, R1 till R15. In x86 assembly, where the Intel and AMD family of processors use x86 assembly, the registers are typically referred to as EAX, EBX, ECX, EDX, ESI, and EDI. So these are general purpose registers. Additionally, there are machine specific registers which allow you very fine-grained and internal access to changing things such as the speed of fans, the power, temperature controls settings. So these are called machine specific registers, which are specific to the processor, not necessarily specific to the processor family. Then there are registers with some special functions. So one of them is the stack pointer that we shall discuss later. Then we have the program counter. We all know what the program counter stands for, chapter 1. It essentially points to the address of the currently executing instruction. Then there is also a return address register that we'll come to later. So now let's take a look at memory. So memory, all assembly language programs, or all programs for that matter, look at memory as one large array of bytes, one huge, very large array of bytes. Each byte or each location has an address. So the address of the first memory location, the first byte, so we start counting from 0 in computer science. So the address of the first byte is 0, the address of the second byte is 1, similarly the address of the nth byte is n minus 1. So the program is stored in a certain part of memory, so we can assume that the program is stored over here, and the data is stored in some other part of memory, so we can assume that it's stored somewhere over here. So every binary assumes that the entire memory belongs to itself, and so we are up till now not discussing what happens if you're running multiple programs at the same time. We will come to that slightly later. At the moment, we are only talking about how an assembly program or a binary program would actually view memory. And the program counter contains the address, which is essentially the address of the location of the current instruction. So the current instruction starts from here, so this address is contained inside the program counter. So now let's take a look at how data is stored in memory before we actually discuss more about assembly languages. So there are four mainly, there's different kind of data, but the typical data types that we use in C are of this type. We have a char or a character, which is 1 byte. We have a short integer, which is 2 bytes, a regular integer, which is typically 4 bytes, and a long integer, typically 8 bytes. So both C as well as Java follow this convention. So the question that we need to answer is that in memory, how exactly is data stored? So how is a 4 byte integer stored? So what we do is that we save the 4 bytes in consecutive locations in memory starting, so let's say first location is I and the last location is I plus 3. So there are two ways in which we can store data. So one is called a little endian representation. This is used in the ARM and x86 family of processors. Here the least significant byte is stored in the lowest location. So we shall see a visual depiction of this on the next slide. Then we have the big endian representation used by Sun Spark and IBM Power PC. Here the most significant byte is stored in the lowest location. So let's take a look at examples of this. So let's consider an integer of this form that actually contains 4 bytes. It's in a hex notation. So one digit is 4 bits. So as a result, 2 digits is 1 byte. So this is the first byte, second byte, third and fourth. So in the big endian notation, the way that we actually store it is that the most significant byte, the MSB, is actually stored in the lowest or the smallest memory location. So first we store 87, then we store 65, then 43 and then 21. In the little endian location, we store the least significant byte first. So we store 21 over here, then 43, then 65 and then 87. So what is different is the order of the storage of bytes, and so this is a matter of convention. We can't argue that little endian is better than big endian or vice versa. It's just a matter of convention of how data is stored. So ARM and x86 designers have gone for little endian, whereas IBM and Sun designers have gone for the big endian scheme. So different conventions are there, and the hardware as well as the assembly language writer, the assembler and compiler writers need to be aware of the particular mechanism or scheme that's being used. So now that we know of how individual integers are stored, we should also take a look at how arrays are stored. So an array of integers is basically a set of n integers. So let us consider an array of integers a100. So way it is stored is actually very simple. We store the first element of the array a0. Then in a consecutive location we store a1 and a2 and a3 and so on. So if one integer is 4 bytes, the entire array would take 400 bytes, and we save the integers in consecutive memory locations, right? And each integer is stored in either a little endian or a big endian format depending upon the convention followed by the processor. Now an interesting question arises that how do we store a two-dimensional array? An array that has both rows and columns, how do we store it? So there are two methods, row major and column major. So row major scheme is used in high-level languages such as C and Python. So here what we do is that we store the first row as an 1D array, then we store the second row and so on. So let me just show you with an example. So let's assume that this is a 2D array with rows and columns. So a 2D array is a matrix. So what we do in a row major scheme is that we first store the first row. Then we store the integers belonging to the second row. Then we store the data belonging to the third row. The other scheme called column measure, which is followed by programming languages such as Fortran and MATLAB, they actually store the first column, then the second column, and so on. So there are trade-offs between row measure and column measure, but we are not in a position to appreciate this right now. We'll discuss more of it in chapter 10. So what exactly is column measures? In column measure, the first column is stored. Then the second column is stored. And then the third column is stored, right, in memory. So both of these approaches are sort of opposites of each other. In one case, we traverse the array row-wise. In other case, we traverse the array column-wise. So there are trade-offs in this. So it depends upon the way that we write programs. So we'll discuss more about this in chapter 10. But what is important to know, so the main take-home point here is that all programs, including assembly languages and processors, fundamentally assume that the memory is one large array of bytes. To save an integer, which is a 4-byte integer, we take 4 consecutive locations in memory and save the integer in either a big endian or a little endian format. To save an array of integers, we can save it in any form that we want, row measure or column measure. So let's assume we want to save the array A100. If one integer is 4 bytes, we need to take up a space in memory which is 400 bytes and save the 100 integers. And each integer can be saved in either the big endian or the little endian format. Now let us take a look at the syntax of assembly language. So syntax basically refers to the way that assembly language is written. So a typical assembly file looks as shown over here. So there are many kinds of assembly languages for many kinds of architectures, many kinds of ISAs. So clearly all of them have different formats, sometimes very different formats. We will discuss the assembly structure of the GNU assembler, which is very common in Linux and Mac OS. Even other assembly files in diverse operating systems such as Windows have a roughly similar structure, even though there are differences. But we only want to discuss the generic parts in this lecture. So if I consider a certain assembly file, the first part of the assembly file contains some meta information like the name of the original program that that this assembly file corresponds to. The .text section corresponds to all the instructions, and the .data section corresponds to all the data that is accessed by the program, all the constants particularly that are accessed by the program. So the important point to note over here is that an assembly file is divided into different sections, and each such section is demarcated with identifiers. In the GNU assembly case, these identifiers are .file, .text, and .data. So as mentioned in the previous slide, .file refers to the name of the source file. .text section, the text section contains a list of instructions, and the data section contains the values of read-only variables and constants. So the structure of an assembly statement is typically like this, that we have an instruction and then we have a list of operands which are the arguments of the instruction. Each instruction, as described before, corresponds to typically one machine instruction, and the operands can be of different types. For example, they can be a constant. So a constant is also known as an immediate. A constant, examples of a constant are 3, 4, 5, numeric constants, character constants, string constants. So in assembly language parlance, they are typically referred to as immediates. the operands can also be registers, and the operands can also be memory locations. So we'll look at more of how to specify different kinds of operands. So let's take a look at examples of instructions. So the first one is a sub instruction, a subtract instruction. What this achieves is that it subtracts the contents of R2 from R1 and saves the result in R3. So if we want to write, we can write this in this form. So this is similar to similarly, the next assembly instruction is similar to R3 is equal to R1 multiplied by R2. So in this sense, this is like a high-level programming language, albeit the syntax is slightly different. So the destination always comes first. So the first operand is typically the destination, and the next two operands are the source operands. So the source operands in this case are specified using registers, but that need not be the case. So we'll take a look at that in the next few slides. So the generic, but this is one kind of the previous, these two assembly statements are only one kind of assembly statements. There can be many other kinds as well. Let's take a look at some. So we can have a generic assembly instruction followed by a comment. So there are two ways of commenting that we will look at in this chapter. The first comment starts with an at, so anything after an at is a comment, or we can have generic C style comments with a slash star and then a trailing star slash. So the comments can always come at the end of a statement, or you can have an entire line with the comment. The assembly statement itself can be an assembly instruction, or we can define a constant, or we can have an assembly directive, which is essentially an instruction to the assembler to do something special. So we'll discuss that later. And the entire assembly statement inclusive of the comment can be preceded by a label. So label can be thought of as, so it's similar to a label that is used in a goto statement in C. It uniquely points to the assembly statement that is after it. So we can have a label and then a colon and then specify the assembly instruction. Later on, if we want to come back to this label, we just need to have something to the effect go to label, and the control will jump back to this particular label. So label is an optional argument. It's not required all the time, but whenever we want to jump to this particular statement from anywhere else in the program, we can use the label to indicate this particular line. So a label is essentially the identifier of a statement. And as I told you before, a directive tells the assembler to do something. You know, maybe let's say declare a function or declare the fact that a new section is starting in the file. So there are many kinds of directives. We'll discuss that gradually. So in the generic statement structure, we have already looked at the assembly instruction part and the comment part. So we can have many kinds of instructions. So primarily four kinds. So we can have data processing instructions. So these instructions are typically arithmetic and logical instructions. They can be used to add, subtract, multiply, divide numbers, perform arithmetic operations on them. Also, they can be used to compare two numbers and store the result somewhere else. We'll discuss where that somewhere else is. Also, do Boolean operations between the values stored in registers, namely a logical or, a logical and, or a logical not. So these are all Boolean operations that can be done. by this family of instructions called data processing instructions. Similarly, we can have data transfer instructions. These instructions transfer values between registers and memory locations. So these are also very useful to bring in data from memory to registers and also to move data between registers as well as move data from registers to memory locations back. Then we of course need branch instructions to implement for loops, while loops, if statements. So branch instruction is typically like this, that we branch to a given label, where the label is what we looked at in the previous slide. It uniquely identifies an instruction, an assembly statement. Along with data processing, data transfer, and branch instructions, we can have special instructions to interact with peripheral devices and other programs or set machine specific parameters or essentially access special parts of the computer system that are otherwise not accessible to high level programs. So these are special instructions. Let us now discuss the nature of operands. So let's begin by classifying instructions and defining some basic terms. So if an instruction takes n operands as input, then we say that it's in the n address format. For example, this instruction over here, the add instruction, takes 3 operands as input. So we say that it's in the 3 address format. So similarly, we can have instructions in the 1 address, 2 address, and we can even have 4 address format instructions. So an address format basically refers to the number of operands that an instruction takes. Let's then look at the addressing mode. So the method of specifying and accessing an operand in an assembly statement is known as the addressing mode. So we'll see there are many kinds of addressing modes. For example, in this assembly statement over here, each operand is a register based operand. So the addressing mode is a register based addressing mode. So now let's introduce the register transfer notation. We'll actually require it to specify the semantics, the way that our assembly instructions work. So in the register transfer notation, let's take a look at the most basic notation over here. R1, the contents of R2 being assigned to R1. So this basically, so this arrow indicates that the direction of data transfer is from R2 to R1. So this says that transfer the contents of register R2 to register R1. So we can have a slightly more complicated representation as well. So this representation says that add 4 to the contents of register R2, essentially add an immediate to the contents of register R2, and then transfer the contents to register R1. The last expression is slightly different. So what this says is that we first access the contents of register R2, and then so assume that the contents of register R2 are, let's say, 8. We access the integer, the 4-byte integer, whose starting address is 8, and then we subsequently read 4 bytes starting at location 8. So essentially we read the bytes at location 8, 9, 10 and 11. So these 4 bytes make one integer. This integer is transferred to register R1. So in this case, we are actually accessing a location in memory. The address of the location is specified in register R2. So if we read the definition that's mentioned over here, it says we access the memory location that matches the contents of R2. So in this case, in the example, the contents of R2 are 8. So we start from memory location 8 and read 4 bytes starting at 8, 9, 10 and 11. So 4 bytes make one integer, and then the integer is stored So in this case, the integer is the data that is coming from memory. This is stored in register R1. So this is a memory load operation. So this operation is called a memory load because we are loading data from memory. So let's take a look at some of the very basic addressing modes. So let V be the value of an operand and let R1 and R2 specify registers. So the convention is always that R1, any variable starting with R always specifies a register. So let's take a look at the immediate addressing mode. In the immediate addressing mode, the constant itself is the value. For example, 4, 8, or a hexadecimal constant over here, which is 0x13, it's 19 in decimal, or even a negative number, can be anything, can be any kind of a constant. So when a constant is directly used as is, for example, if I have an instruction of this form, add R1, R2, and 4, this particular operand is using the immediate addressing mode because the constant is specified as is. Similarly, we can use the register direct addressing mode where the value of stored in the register is what is being used. So in this case, R1 is using the register direct addressing mode. Similarly, we can use the register indirect addressing mode, something that we had seen in the previous slide in this particular point. For example, we can, in some variants, in some assembly languages, we can write a function of this type, add R2, R3, and R1. So in this case, R1 actually contains a memory address. This will be used to access memory. We will read 4 bytes from there, the size of an integer, and this will be added to the contents of R3 and finally be saved in R2. So this is called the register indirect addressing mode because what the register contains is actually a memory address. The address is sent to the memory, we get contents from the memory and then use it in an instruction. Similarly, we can slightly extend this to create the base offset addressing mode. So in this case, the actual value that is being used by the program is actually R1. So in this case, let's consider an example and then explain the theory part of it. So let's consider this operand over here, which is using the base offset addressing mode. So what this basically says is that we take the contents of R1. So let this be the contents of R1. And then we add it with the constant here 20. So assume that the contents of R1 were 8. So we add 8 and 20 and we get 28. We use 28 to access the 28th location of memory, and then we read 4 bytes from the 28 to the 31st location, and these 4 bytes are then used by the program. So this is a base offset addressing mode because in this case R1 contains the base address and the offset is 20. So we add both of them, we get a final address that's called the effective address, which is used to access memory, and then we get the contents of an integer from memory. We read an integer from memory, and this is used by the program. So the same thing is shown over here, that we take the value of R1, we add it to the offset. The square brackets indicate that the address is sent to memory and we read the contents from memory, and this is the final value that we use. So let's show the register indirect mode once again using a set of better pictures. So as mentioned over here, we take the value of R1 and whatever is the value of R1, we use it. We first read it from the register file, and then we use the value to access memory. So let's assume that, for example, R1 contained 32. So we access the 32nd location in memory and read 4 bytes. So for simplicity, we have not shown 4 entries, and we finally read the value out. Now let's discuss the base offset addressing mode. So this mode will be very useful for implementing arrays. So the main idea over here is to actually use a register called the base register. In this case, in this example, it is R1. So R1 is used to access the register file. From the register file, we read the contents of R1 and we add it to the offset. So we get an address as the output, and this is called the effective address, but let me just call it as the address for the time being. The address is used to access memory, and finally we read 4 bytes from the memory. So the 4 bytes are part of the single cell. This is drawn to enhance readability. So the 4 bytes are the value of this particular operand. So what exactly is the base offset addressing mode again? We have a register and an offset. We read the contents of the register, add it to the offset. This gives us an address. We use this address to access memory. So for example, let's say the address is 28. So we access the 28th location in memory and read 4 bytes. And these 4 bytes are the final value of the instruction. So let's discuss some more addressing modes which are not very frequently used, but nevertheless they are common enough that we should discuss them. And especially when we take a look at the x86 instruction set, we would find these addressing modes to be extremely useful. So one of them is the base index offset addressing mode. So in this case, we instead of one register, we have 2 registers. So we have a base register, which in this case is R1. We have an index register, which is R2 in this example, and we have an offset, which is an immediate. So we add the contents of the 2 registers and the offset. We get an address. This address is used to access memory. And we read the value out. So this is the value of the operand. So one example would be 100 R1 R2. Here R1 is the base register, R2 is the index, and 100 is the offset. So note that this sign of braces, the square braces, are used to indicate that the contents within the braces refer to an address, and once we add the braces, we are supposed to access memory with the address and treat the locations in memory as containing the value of the operand. So we can again have a memory direct addressing mode, which is not there in most ISAs, but it's there in x86. In this case, if we know the address of the memory location, we can directly specify it. We don't need to add it in a register. Instead, we can directly specify it. So in this case, if this is the address of the memory, we directly specify it and enclose it in in square brackets or in braces. And this indicates that we access memory with this address, and the subsequent 4 bytes contain the data of the operand. Lastly, let's take a look at a certain variant of a register indirect addressing mode, which is actually very useful. It's called the PC relative addressing mode, where instead of using a general purpose data register, we use the program counter. We treat the program counter as a register. So in this case, we take the contents of the program counter, add an offset to it to get an address, and we use the sum of both to actually access instruction memory. So let this be the memory in specific the instruction memory. So then the next 4 bytes uh, are actually the contents of the operand. So the next 4 bytes are typically an instruction. In a 32-bit system, which we assume to be the default in at least in this book, this is so these 4 bytes from the PC will typically point to an instruction. So we will find this addressing mode very, very useful. This addressing mode will be found to be useful especially while implementing the concept of if statements, for loops and while loops in assembly, that we'll be able to change the PC, the program counter, to essentially we'll be able to change its value and jump to different points within the program, which is exactly what an if statement or a for loop or a while loop do. So let's keep this discussion at this point, and when we go into the nitty-gritties of assembly language, we'll come back and revisit this point. So let's take a look at the base index offset addressing mode once again with a better diagram. In this case, we have 2 registers. We have R1 and we have R2. So both the registers are used to access the register file. We add their contents plus the offset. Then we access memory and we use the value.